to my example of a bimetallic strip. I don't care if you get this on a video or not. And it really doesn't matter which side you heat. It bends the same way. I guess it's not like the thermos bottle, you know.
If the metal was, if you had like a single material and the metal was thick enough, and you heated one side of it, would that cause any curvature in the metal like that? Not that severe. Or...
What do you mean? You say if one was thick and one was thin?
No.
So,
actually, if you had like one material and the plate was thick enough, if you were able to heat just one portion of it, would that cause just enough tension at one side that cause a curve?
In fact, that's how we straighten beams. If you have something that's thick enough, and so the thermal diffusivity is such that it's not thin like this, that it heats through and is almost uniform heating, right? There's something called the BO number in heat transfer. You guys remember that? How many? Oh, okay. The BO, B-I-O-T. Yeah. In any case, if I had a half-inch thick plate and I took a acetylene torch to it and I heated one side for 5 or 10 seconds, the heat won't saturate all the way through a half an inch during that period of time, so the top surface will expand and the plate will bow downward when it's hot. But the material, if I get it warm enough, will start to yield because it's in compression. It's constrained by the material beneath it, which isn't hot. And if it yields and shrinks a little bit, when the whole thing cools, that material and everything becomes uniform temperature again, that material will have a curvature to it, the opposite of the direction that it was when you heated it. In fact, that's how you get residual stresses in thick plates. And I told you didn't have to worry about residual stresses too much if you were below half an inch, 3/4 of an inch. Well, that's because the heat from the welding process, the time of the welding process being on the order of several tens of seconds when you're passing the point, or 10 seconds or several tens of seconds. If it's only 1/4 of an inch thick or 1/8 of an inch thick, it's fairly uniform in heat, and so the thing doesn't distort as much and doesn't develop residual stresses. If it's 3/4 of an inch thick, then you start developing residual stresses. In fact, the boiler and pressure vessel code basically tells you if it's more than 1.25 inches thick, you have to stress relieve it afterwards. And that's because you get that thick and you can build up yield level residual stresses in the material, which can do lots of bad things in terms of fatigue or corrosion or other things, stress corrosion. So it turns out that people if a beam gets bent or something, people come in and it's kind of an art, but they know how to heat these things and they kind of guess the time because they've done this before. And the thing will initially bend the wrong direction and you make the bend even worse when you're trying to straighten it out. But when it yields, when it's bent, when the top is hot and the bottom is cold, when everything comes back to uniform temperature and it comes back, it'll straighten out. I've seen half-inch plate take a 45-degree angle by repeated bending, and I mean a 45-degree angle over a distance of a half an inch. I mean, it'll come in and it'll take shape like that by repeated welding in the same spot. We did it unintentionally in the lab once. We were just running around in circles with the gas tungsten arc, and we had a half-inch steel plate. And after about an hour of going around in circles, the thing had bent up, the half-inch steel plate had bent up at 45 degrees over about a 1-inch distance, okay? Cincinnati, the stadium where the Cincinnati Reds play has got some big beams. These are the largest rolled beams in the world. In fact, I don't even know they're rolled anymore because the Bethlehem Steel plant's closed where they used to roll them, but they were like 36-inch web. And one of these, they were lifting it up to install it on the stadium, in the roof of the stadium, and the crane had a problem and dropped it. No one got hurt, but the beam all of a sudden was bent like that. And it was a 1-year lead time before Bethlehem Steel could roll them another beam because they didn't put those rolls in very often. Not a lot of people needed that type of beam. and this one was particularly long. And I met the guy who was the welding engineer out of Ohio, who basically went in and used oxyacetylene torches and took this beam that was bent at like a 30-degree angle on the web, and he straightened it back out by just heating it over. It probably took a week to do all this. A number of years ago, about 20 years ago, a truck driver fell asleep coming over the Mystic Bridge, the Tobin Bridge, and he ran into one of the columns. He was on the lower deck coming into Boston, and he ran into one of the columns, drifted off, ran into the columns, bent the column, and they basically ended up doing the repair, and part of that repair was just heating the beams up to straighten them back out. So, I mean, the ship plate sometimes they'll curve it by just heating it. It's a very slow process, and it takes a lot of certain art. You can't do that with HY80 because you'll destroy the temper of the quenched and tempered steel. But in the carbon steel, you can do some pretty amazing things in terms of bending plate. Okay, so here's just kind of a review of last time. I'm not sure that I'd given you, I put the Stefan equation up, and I may have given you the one where it was load rather than pressure. If the pressure is F, which is load per unit area, right, times the time, that's equal to 3/4 the viscosity times the radius squared, if this was a simple disk, times 1/h2 squared minus 1/h1 squared, where h1 is the initial thickness and h2 is the final thickness. And it explains this equation only has two significant parameters in terms of changing the force-time product. One's the viscosity and one's 1 over the thickness, 1 over the thickness squared. And you can get stronger joints by making thinner joints, which is what happens in Johansson blocks. You get a super finish, a mirror polish on those surfaces, and you put a little bit of liquid in there, like the adhesive, with a fair amount of strength, depending on the viscosity of the adhesive and the thickness of the joint. However, it turns out virtually all adhesives work by, you have to first apply them, which means you want them in a low viscosity form, right, in order to spread into the joint. And you might say, well, that's not too hard. I mean, Elmer's glue is a little bit thick, and epoxy might be a little bit thick. But it gets to be a real problem if you're doing something critical, like, let me borrow that for a second. Let's say this was a beer bottle, and you want to put the label on the beer bottle. Okay, now this label is just papered on, but actually they did have to adhesively bond it when the paper came around to the, to the joint back here, right? But remember, your beer bottles, they basically just put the label on there. Well, anybody know how fast they bottle beer? It's about one case a second. Is that right? Yeah. If I gotta get this right. It's been 25 years since I've been through a beer bottling plant. But they basically have a great big circular thing, and the beer bottles come in lined up, and they go into this track that holds about 100 bottles, and the bottles get filled, and they're coming out of there at about, 1 bottle a second. Okay, I was about to say a case a second, but it's about 2 cases a minute, okay, coming out of this machine. I mean, it's a bottle a second. Well, you actually can't even fill the liquid at 1 bottle a second, which is why you have this circular buffer, if you will, that's holding them in there for a second. But in that whole process, when the labels come by, they're slapping the labels on there in a fraction of a second on the label machine that applies the labels, because these things are coming out of there at 20 miles an hour or whatever. And that means that you've got several tens of milliseconds, or maybe you've got a tenth of a second, to apply the adhesive. Well, you start going through the Stefan equation, and I gave you some examples, or put some examples up. You've got to have a pretty low viscosity adhesive to be able to make the joint in that amount of time. If you're talking, right, A is the radius of the disc. This is just 2 discs being joined, 2 circular discs. A is the radius of the disc. In any case, you need low viscosity, if you're trying to do things at very high speeds. And there are times that you're trying to do things at very high speeds for applying an adhesive. But then after you've made the joint, you want to harden it up, and you can easily get 10 orders of magnitude, and 10 orders of magnitude is usually enough to go from 1 second to 100 years. Okay? That's usually 100 years is good enough for an adhesive joint. And you do that by three things: solvent removal, solidification, and chemical reaction are the three basic ways. And if you now go out and think of any adhesive, just like we used to say when we studied symmetry and crystallography, the students used to say, you never look at bathroom tile the same way again. You always look for the symmetry patterns. Hopefully now, whenever you use an adhesive, you'll think, well, is this solvent removal or chemical reaction or solidification that I'm using to change the viscosity of the stuff? Okay, those are the three basic ways. And frankly, this approach is a lot more practical from an engineering sense of how do you make joints than worrying about the Leonard-Jones potential and gluons and nuclei and protons and things like that. Basically, you're just looking at the properties of the viscosity of the material. Now, I also talked about mechanical interlocking as a second type. And mechanical interlocking, I would like to end up with a rough surface rather than in something like type 1, you generally want a fairly smooth surface, but with mechanical interlocking, you want a rough surface. You roughen up some things in order to make the adhesive work better. Oop. A little too much there. Okay. So here is something out of the Handbook of Adhesives on surface preparation of metals, and this actually has to do with anodizing aluminum. Are you familiar with anodizing? I mean, you've seen anodized aluminum, but do you know how it works? Basically, you put the metal in a liquid bath, and you pass a current through it, and it's called anodizing because the anode corrodes. The anode's positive, and you get corrosion at the anode. By passing the electric current through it with the right type of solution, and this happens to be a chromic acid anodized on aluminum, you will grow an oxide film on the aluminum, but you'll grow it in a controlled way. However, the current has to still get into the aluminum metal, and the way the oxide film grows is essentially a very porous mass of oxide that starts growing out at about 20 nanometers, 200 angstrom wide channels, and it grows up, the little fingers grow up, and it forms kind of honeycomb type cells. They're not uniform honeycombs, but you can think of it as honeycomb type cells of aluminum oxide growing up. And if you do it, depending on how you do it, you can get thicknesses that are like 3 or 4 thousandths of an inch thick. In fact, they sometimes call it a Martin hard coat, is a type of anodize they put on where you get some, basically hard aluminum oxide, 3 or 4 thousandths of an inch thick, and it gives you good wear resistance on aluminum. We're more familiar with anodized aluminum where people color it and things like that. Well, how do they color it? They grow the oxide, which is porous like this, and then they inject a dye into these holes, basically. They coat it with a colored plastic, and that gives a nice sealed surface. That has good corrosion protection as long as you don't break through all that. Well, it turns out for adhesive bonding, this is perfect in terms of a nice porous surface to get mechanical interlocking if I get my adhesive down in there. And so it turns out for adhesive bonding, I like to anodize aluminum, and I can do other things to give you an idea of what the structure looks like. That's the scanning. These are scanning electron micrographs of the anodized surface. It's a very rough, very tortuous surface. Now, we actually use this type of anodizing and stuff for other things. You can make, with both tantalum and aluminum, you can grow these things, and you can make capacitors. That's why we use aluminum and tantalum capacitors. We grow an oxide surface, which has lots of surface area, and lots of surface area allows me to store lots of electric charge on an insulator. And so I basically anodize the surface of aluminum to make capacitors. If I want to use anodized aluminum for corrosion protection, though, I've got to do something to what we call seal that surface. I mean, I can put plastic, I can impregnate it with plastic, because if I don't, otherwise I just got a hole through that honeycomb right to the metal underneath. And I remember once, probably 20 years ago, it was the first time I'd ever been on Cape Cod. Some guy called me up and he wanted me to look at his sailboat. This is the middle of the winter. Because he just bought this, $500,000 sailboat, and it was in storage, but it was only a year old or a summer old, and it was already starting to show white rust on the anodized aluminum rails. And the aluminum rails were actually built into the wooden frame of the, you'd call the edge of the boat, the what? Gunnel, the gunnel, right? And to take these things out, you're going to have to completely redo all this custom woodwork of the gunnel. And he wanted to know why this was happening. So first time I was ever on Cape Cod, it was a snowstorm. I was driving through a snowstorm to go look at this boat in storage. And I went and looked at it, and sure enough, someone had anodized the aluminum, but they forgot to seal it. And if you look at anodizing aluminum for architectural applications, you have to seal it. You can seal it by putting a polymer coating, basically painting it. Or more typically, after you've anodized with the electric current, you've got this porous mass, you basically put it in boiling hot water. In boiling hot water, you will actually close up the cells. You'll corrode it enough, but you'll close up the cells. Now I don't have an electric current that requires that the cells stay open. As long as I'm passing electric current, I have to have a conductive path, and the current will keep a path open if I anodize that way. But in any case, so if I anodize the surface, I get a nice rough surface, wonderful adhesive bonding properties on aluminum. Now, it turns out for other materials, I can add chromate conversion coatings, which are not quite as thick. And I don't like to do that as often now because the chromates contain hexavalent chromium, which is a carcinogen. But still, some of the chromates have excellent corrosion resistance properties, and so we still use them in aircraft and things like that, aircraft parts, even though we got environmental problems in their manufacture. But I also, it turns out right after World War II, people found that they could make steel parts, form some complex steel parts by what they call ColdHeading. And this is an example of a cold-headed part. This happens to be, I got years ago when I walked through a cold-heading shop in Pennsylvania. Okay, but this is just a, oh, the wrong way. This thing didn't focus very well. Far away. Okay, so this is actually a threaded. Let's see if you can see the thread in there. Yeah, you can see the thread a little bit in there. So you put a screw in here, and this knurled part goes into a piece of wood, and this is for assembling furniture, right? It's just a simple little cheap part so that you can put a metal bolt into a piece of furniture. And you got the shoulder here that provides the strength. So you put this in the back side and put the bolt through this side, and you get a very solid attachment. Well, if you had to make these things by machining the whole part, it would be very, very expensive. But you go to the hardware store, and these types of parts are dirt cheap, right? A few cents. Well, it turns out that after World War II, people learned that they could phosphate the surface of steel. Just put it basically in phosphoric acid. What's the most common form of phosphoric acid that we use? We actually offer it to you for breakfast. Coca-Cola or Pepsi-Cola. It used to be called phosphates. It's basically phosphoric acid. It's a very high grade of phosphoric acid. It doesn't have any of that arsenic impurity in it that the normal phosphate rock has. That's another story. We can tell you how they make phosphoric acid for Coca-Cola. But in any case, they found that if you basically dip the steel in a phosphoric acid bath, you would form a coating of iron phosphate on the surface, which was very rough, just like that anodized surface. And then they found if they used zinc stearate And stearates are basically organic fatty molecules, okay, long polymer chains or organic chains. I think stearates have 18 or 20 carbons in the chain. And basically, stearates are soaps, and it makes an excellent lubricant. And because of the iron phosphate surface, they could basically hold the lubricant on the surface even through very high pressure forming operations. So this thing basically is cold formed in what we call a cold heading machine. And it's a heading machine because you have a little die and you just push it in, and I'll send around this piece, this block that shows you all the pieces that were made. This is the slug of original bar stock. So I've got a piece of 3/8 inch bar stock that they just shear off. So they just feed a 3/8 inch coil into the machine, and the machine shears it off. If you look at that, you'll see it's just a rough sheared end. You can see the shear marks on the end. This thing has been passed around for years. Doesn't feel slippery or soapy anymore, but originally it felt soapy because it still had enough zinc stearate left on it. But people's hands have kind of leached it out since then. It goes into a first sizing die, which basically gives a little indentation on one side and just a flat on the other side, but it squares everything up. Just makes it a good right circular cylinder as opposed to a rough sheared cylinder. Then it goes through and it actually extrudes a little indentation in it. And then it goes through a second extrusion and another indentation, deeper. Now it's getting longer. And then they put the flange on it, and they actually make this thing deeper. And there's a little piece on the end, and you want to cut that out. So the next operation, and I haven't taken the tape off, but there's a little piece of metal in here, which is they punch out the hole in here. And that's the only waste product. That's the only scrap that's produced in making this final part. Then they, I'd have to compare it. Oh, this is the one with the hole in it. So these two go together. The one, if you want to lift up the tape, you can, but there's a little piece in there. And then they knurl it. Then they thread it. Then they plate it. Well, it turns out this thing feeds into the machine, and the machine probably is going like 5 or 6 shots a second for a small part like this. It's sort of like the old, again, you're running into inertia of the heads, but it just goes, you have to, these shops are terrible. They're probably like 120 decibels. You gotta, they don't just give you earplugs, they give you ear muffs when you go through a shop like this. Because it's just tremendous noise as this stuff is just banging out little parts, okay? Now, I say little parts. I was just in Detroit visiting a student the Friday before classes started, and the student's working in a shop where they make axles for GM trucks. And it turns out they make parts that are about this big. And they do it, the final operation, not the whole part, the main part that big in steel, probably weighs a couple of pounds, is actually hot forged. But the final operation, instead of machining it, they have these kind of complex convolutes in this part of the drivetrain. They actually just push in there and just send a steel die cold and just forms the inside of this cup. And the cup, the final steel part, has probably got a 3/8 inch wall, and it's about the size of a little bit bigger than a coffee cup, and a little bit longer, and it weighs a couple of pounds. But excellent precision because you're just cold forming it. And I looked in there, felt, sure enough, it's got all this soap down in the bottom, okay? And the thing about the iron phosphate is it created a porous surface that kept something for the zinc stearate to stay there, and even though the surface in the cold forming gets extended and everything, it just contaminates that surface with the zinc stearate. I mean, in this sense, lubrication is the opposite of welding. Welding, I'm trying to get clean surfaces. In lubrication, I'm trying to dirty up the surface. Even no matter how much I extend the surface, I want the lubricant to kind of still get spread out, okay? So they do it for fairly large parts now, so far as that goes. One of the problems with, well, actually, before I do that, one of the problems in trying to mechanically interlock like this is I have to have adhesives that will wet the pores. So if I have some pore like this in the material, magnified a great deal, and I have some liquid, and the liquid comes in here, but the liquid doesn't wet the material. So here's liquid trying to come into this pore in my solid, and this is a vapor space, right? I actually have surface tension because these things get very, very small, and surface tension becomes more and more important the smaller I become. And basically, surface tension is keeping me from getting everything in there. If, on the other hand, I had a liquid adhesive that wets the surface and it kind of comes in, it will actually be drawn in if it actually wets the surface and flows across the surface, and the surface tension is pulling the material in and essentially will fill the whole cavity. So one of the key things on adhesives is they have to have a lower surface energy. They have to lower the surface energy. They have to wet the material that they're in contact with. And I don't know, I think I skipped last time showing you contact angle and stuff. You guys have seen contact angle before? Of wetting of surface tensions? Let me put it up since I'm seeing it. So if I've got a liquid, hold on, what's going on? Okay, so if I've got a liquid on a surface, I can define a contact angle of wetting depending on the angle at which the liquid contacts the solid. And the surface energies of the solid and the vapor can be given by some vector here pulling in that direction. Surface tension, or the surface energy, can pull in that direction. The solid and the liquid would be this one, and liquid vapor would be that one up there. And those three forces in equilibrium will give me a measure of the contact angle. So that if I just resolve forces in the horizontal direction, going to the right, I have gamma solid vapor equals gamma solid liquid plus gamma liquid vapor sine or cosine of theta, right? Cosine of theta, and that defines the contact angle. Depending on the ratios of these solid liquid of these three surface energies, I can either have a high contact angle or a low contact angle. A wetted surface is one that has a very low contact angle, and a non-wetting material, if you wax your car, the water beads up on the car, right? And that's because wax has a lower surface energy than the water in contact with the steel and everything. That means that for adhesives, I like to have something that has a chemistry such that it will want to wet the solid, form a low contact angle rather than a high contact angle. A high contact angle, I can't even get the liquid down into these pores to make the mechanical bond. A low contact angle is beneficial, unless it's something that you want to bond to. And what types of surfaces have the lowest surface energies? The surface energy of water is about 72 dynes per centimeter, 72 ergs per square centimeter, if it's pure water. What things, wax obviously has a lower surface energy of water. Water won't wet the surface of wax. If I put something in my dishwashing detergent to try to get the water to not bead up on the glass, water will bead up on very, very clean glass. But if I if the glass is very, very clean, don't know, if the glass has got an oil film on it with a low surface energy, if the glass is not clean, the water beats up, and if the glass gets very clean, then the water will spread out because it wants to lower the surface energy. It turns out polymers tend to be very stable. They're covalently bonded, and they don't have a lot of unsatisfied bonds. Okay, metals have tremendously unsatisfied bonds, but polymers don't. In fact, somewhere in here, no, we won't worry about it. I had some. Oh, I didn't bring it with me. Anyway, the surface energy of various polymers and this comes out of the handout that's in your notes on this handbook of adhesives. This guy Zisman's chapter 3. But I can look at polyvinyl fluoride, which basically is a carbon backbone chain with two chlorines rather than hydrogens. So 2 chlorines and 2 hydrogens in the polymer repeating unit, and it has a surface tension of 40 dynes per centimeter. Remember, water has a surface tension of 72. Polyvinyl chloride, PVC, has got 1 chlorine, so this is 2 chlorines, this is 1 chlorine. This is polyethylene, which is all hydrogens. Polyvinyl fluoride has 1 fluorine, polyvinyl fluoride has 2 fluorines, polytrifluoroethylene has 3 fluorines, and Teflon, tetrafluoroethylene, has 4 fluorines. Okay? So if I look at this, they've got it in decreasing surface energy, and it turns out for solids, Teflon has about the lowest possible surface energy of any solid. And therefore, what am I going to have is an adhesive that's going to wet Teflon? Virtually nothing. Water won't wet it. If I had water and I poured it on a Teflon sheet, the water would bead up on the Teflon. And that means that I have a problem. How do I get a good bond? How do I form an adhesive to a plastic? And if any of your parents, none of you are having children yet? Oh, have children? Okay. So have you ever had toys that they break and they come and say, will you fix this?
My son's not that old yet.
Oh, okay. Well, they will. Okay. Fisher Price makes things out of plastic, right? And they will come to you and they'll say, Daddy, can you fix this? And the problem is there's no adhesive that works very well with most of these plastics because the plastics have low surface energy. Plus, the parts that break are the thin parts, and there's no significant contact area. The adhesives don't make primary bonds, they make secondary bonds, Van der Waals type bonds, and they're making Van der Waals bonds on something that's very stable and not very polar to begin with. Why is polyethylene lower than some of these chlorides? Because there's a little bit of polar nature to these, whereas the polyethylene doesn't have any polar groups, in a sense, along that long chain. You get down here, the fluorines are even more stable, and the one that's nothing but fluorine has the lowest surface energy of all. So it turns out a lot of Zisman's article talks about things with very low, he liked to study things that with very, very low surface energy, which is good for lubricity. Okay, and that's what this column is a static coefficient of friction. You can see the static coefficient of friction, Teflon, we know is very slippery. Polyvinyl chloride's got a static coefficient of 0.9. That's pretty sticky compared to these other things. It all has to do with the surface bonds and the surface energy. So it turns out, I've never done this, someday I ought to do this. There is a trick to bond to something like Teflon. I want to get the liquid down into the bottom of the groove. Anybody have an idea how you can do that? You can apply pressure, but if you get to very small pores and you go through, the The surface tension gets more and more important as you get smaller and smaller. We'll get to that later when we get to soldering. But as you get smaller and smaller in those pores, the surface tension fights you more and more, okay, as you get smaller, because it basically goes as 1 over R, where R is the dimension. Well, it turns out if you can't put a liquid down in here because the surface tension is going to hold it back, why don't you put a vapor in there? Supposedly, if you take Teflon with its rough surface like this and you expose it to wet steam or condensing steam, so you want this to be, if your steam is up here at some temperature T2 and you have your Teflon chilled a little bit, you'll condense the steam, and where's the steam? The gas molecules can get down here, and if they condense down here, they're going to grow they're going to nucleate and grow from the bottom, and surface tension is going to keep the water that condenses down in there. So supposedly, if you do this and you precondition the surface with a vapor in here, and then apply the liquid, the stuff is going to stay down in here. And then if you do something to freeze it, now if this is water, you have to freeze between, and you'll basically be able to make water stick to Teflon if you freeze it, or make ice stick to Teflon. Now you could do that with something else rather than water as your liquid. The easiest thing in the laboratory would just be to prove it in a freezer with water. But you could precondition surfaces in order to make them more receptive to forming adhesive joints. I haven't done it, and I don't know that anyone does it this way, but that's just a way to think about doing it. Another problem when you don't have adhesion is you tend to get a bunch of pores, and they'll tend to all line up right where you don't want them on that interface, and you'll get a weakened interface. And in fact, that's what happens when you take Scotch tape, and the first time you stick it to something, it sticks pretty well. But you know, this happens to be a piece of plastic, and the Scotch tape doesn't stick as well to that plastic as it does to this wood. Why? You can actually, did you hear that? You can hear it on the wood. It's softer on the plastic. Why? Lower surface energy. The stuff doesn't stick as well to a low surface energy surface. But if I keep on doing it over and over again, all I'm doing is I'm picking up all the contaminants on here, and I'm contaminating the Scotch tape, and you know that eventually the Scotch tape doesn't bond as well because it's getting a contaminated surface. Contaminated surface, you're lowering the surface energy by all the contamination you're picking up, and you're getting to the point where you're leaving these pores behind, and the thing just doesn't bond very well. There is an application where someone had developed a way to make an adhesive that was good enough that it came off easily, and that's the story of Post-it notes. If I rip the Post-it note off, I don't rip the paper. The first time they tried to make little Post-it note-like things at 3M, they made adhesives, and paper against paper, the paper's not very strong. And they would have a problem because the bond was strong enough that basically it would rip the paper a certain, significant fraction of the time. And so they had this idea to make Post-it notes, and it just didn't work. And so finally, a guy came up with this idea, and basically, if you looked in a microscope at the adhesive on Post-it notes, you'll find it's a series of little dots of adhesive. It's not continuous adhesive. In fact, I think they put it on there as a two-phase polymer mixture. They coat it on there as a single liquid that phase separates so that you get one area which is sticky adhesive and the other is not sticky. So you actually have a perforated surface on your Post-it note intentionally like this. And I can remember one time I was just playing around and sitting in a meeting or something and bored to death. And I just kept on playing with the Post-it note, and it was a dirty table. And I kept on putting it down and picking it up, kind of doing this little experiment. And I turned it over and looked at it, and you could see the pattern on that particular brand of sticky, right? That you could see the adhesive pattern on there. if you contaminate it enough, right? So that's a case where you want the right amount of adhesion, but not too much adhesion. Okay, what do we use for adhesives? Well, that's why I brought this guy back. We use virtually anything for adhesives. Anything that has a low enough surface energy to wet something else. Clean metal surfaces are the easiest thing in the world to wet because they have very high surface energy to begin with. Almost anything you put on the surface is going to lower the surface energy and contaminate it. Polymers, ceramics, and things have lower surface energies, and so things tend to not bond quite as well unless you use type 2 adhesive bonding and get more mechanical interlocking. But if let me get to the index in here. If I look in here, the first 3 or 4 chapters are kind of the fundamentals, section A, but section B, which is most of this handbook, talks about adhesive materials. And it turns out the first thing is inorganic adhesives and cements. Okay, that's basically Portland cement. The second one is animal glues. I mean, they talk about taking the horse to the glue factory, right? Because it turns out virtually any proteins tend to have fairly low surface energy. So most proteins, and actually a lot of starches also, have relatively low surface energy, and so they will contaminate surfaces pretty well. Another one is gurry. Anybody know what gurry is? You have to go to an unabridged dictionary to find, but gurry used to be an important part of the Massachusetts economy. Gurry is fishing offal, okay? O-F-F-A-L. What's offal? That's the leftover guts of the fish. When you fillet the fish, you got the heads and the backbone and the fins and everything. And if you ever felt any of that stuff after it started to decay a little bit, it actually gets sort of sticky as it starts to dry out. When it's wet, when it's still wet, now you may not be touching it a lot, but it does get sticky, okay? But that's what gurry is. And I can remember 25 years ago when I used to mail my taxes in Massachusetts, they give you a little envelope. Well, I'm not foolish anymore. I don't lick that envelope anymore. It tasted terrible. And I'm convinced that they were using glue made from the fish factory, okay, from the gurry at the fish factory. So, you know, it's bad enough to have to pay taxes in Massachusetts where you don't get anything for it except rude public servants. But, you know, to have to pay the taxes and then it leaves a bad taste in your mouth to mail the taxes, right? In any case, gurry fish glue is chapter 8 in that book, okay? Now, this is Norland Products, North Brunswick, New Jersey. Fish glue was the first liquid glue that reached commercial importance and was the forerunner of all household glues. Many of the original industrial applications developed because fish glue was liquid and easily replaced animal glues, which required a heated glue pot. Okay, fish glue has been used for over 100 years. Okay, well, we tend not to use it much anymore because they closed George's Bank and everything else. But fish glue, Casein glues and adhesives, C-A-S-E-I-N. Anybody know what casein is? Basically, it's the byproduct of dairy products and stuff. It's the whey that's left over from curds and whey when you make things. It's protein that comes out of the milk. Soybean glues, blood glues. What else are you going to do when you slaughter these animals? You take the blood and you make glue out of it. It turns out there's protein there. Starch-based adhesives. You know, we had soybean before, but starch-based, you can use old corn stalks. Then cellulosics, and then resins and rubber-based. They're starting out here with some of the less expensive stuff. And the cheapest adhesives will go for about 10 cents a pound because it's just old blood or fish guts or something like that, okay? Now, one of the problems with those things, a lot of them are fairly water soluble. And if you get down to the end of this thing, they have vinyl acetate ethylene copolymer emulsions, ethylene copolymer based hot melts, polyvinyl acetal adhesives. We have the cyanoacrylates, the super glue. So, super glue is not cheap. I mean, you price it out. I mean, how many, you get a tenth of an ounce for $2 or $3, right? Is it? Well, a tenth of an ounce? Well, anyway, whatever. It probably is around 40 or 50 bucks a pound, if not a couple $100 a pound, I would think, for super glue. But the best adhesives get to be very, very pricey. To get water-based, you're probably going to have water-resistant adhesives. You're probably up to $10 to $15 a pound. And if you're talking about aerospace adhesives, you're probably talking $400 a pound. You're talking very, very sophisticated chemistry, organic chemistry. You have other things like silicone sealants, all kinds of things. As long as they have low surface energies and will wet a surface, you use virtually anything, from 10 cents a pound to $400 a pound. Now, to tell you the story about people who thought they could do things inexpensively, in the 1970s, we had our first oil crisis, and the automotive companies learned that people weren't expecting to just buy a car every 3 or 4 years. You guys are too young, but when I was your age or younger, we're back in the 50s and 60s, it turns out people that bought new cars wouldn't expect to keep them more than about 3 years. And you never heard of warranties, of drivetrain warranties for 7 years, because cars were sort of expendable. If you could afford a new car, you'd probably buy a new one every 3 years. And if you couldn't afford a new car, you'd drive an old car, and the cars were junk after about 6 years. You just scrap them. But after the first oil crisis, and the price of oil went up, and the price of transportation went up, people started clamoring for cars that lasted a longer period of time. And I remember I used to be really irritated when I worked at a steel company, and I knew that they used to put in just carbon steel tubes for the muffler systems, okay? And how many times when I was your age did I replace the mufflers? Like every 30,000 miles you had to replace your muffler system. It might have been dirt cheap, but it was a pain in the neck, and I almost killed myself once when I was underneath there on a creeper, and I had it blocked up on one of these little tripod things, and I was there moving the wrench, and I moved it kind of hard, and the tripod started tilting, and the car was about, actually I wasn't working on the muffler at the time, I had the tire off, and so if, ordinarily if it would have fallen down on the tire, but in this case there wasn't a tire on the axle, or a wheel on the axle, and it would have come down on me. And so I'm sitting there holding the car from tipping with one hand and trying to inch myself out from the creeper with the other hand. My wife, I'm not sure if I've ever told her this story. We had probably one child at the time, maybe 2 children. And I was interviewing, we were down there interviewing for my first job. And so I was fixing whatever it was underneath the car. And of course I had an old beat up car. I used to carry a creeper with me in the trunk, right? And tools, right? This is kind of the quality of my vehicle, but so we were traveling, we were away from Boston, but I had all the tools with me. And I finally got out far enough that I could quickly roll, and the car came slamming down where I was, right? And if I hadn't been able to do that, the car would have come down on me if it had tipped over. Anyway, it used to irritate me no end that they would use carbon steel for the muffler systems, because I knew for an extra $10 a vehicle, they could put in a aluminized or chromized steel, or put stainless steel in there, and the thing would last for 100,000 or 150,000 miles, which is what you get now. And now, of course, back then you could pay $30 to replace your whole muffler system. Now it costs $700 to replace your whole muffler system. But in any case, people were looking for durability in automobiles starting in the 70s. The automotive companies started to respond, and one of the ways they responded was to use galvanized steel. Well, the problem with galvanized steel is they really didn't know how to weld it at the speeds they were used to. But they had to go to galvanized, because otherwise you'd show red rust within 24 months. In fact, Honda, in 1973 Honda Civic, its reputation was the biggest piece of junk in the world, because it would show red rust within 12 months. And Honda developed such a terrible reputation in the early 70s as the junkiest car in the world that they basically developed a corporate culture. And now it's a matter of pride that they have to be the best quality car that doesn't have all these problems. And they will go to lengths that other automotive companies won't do. And that's why they make reliable, good cars today. Because they started out with the reputation as absolutely the biggest piece of junk that you could imagine, okay? And that was 30 years ago. So anyway, they go to start using zinc, but they have welding problems with the zinc. So what they started to do, they said, well, particularly on the hem flange of the door, this is where the outer panel of the door and the inner panel come together, and basically they would just fold it over, and they used to weld it. But when they welded it, they would weld it so that the spot weld wouldn't mess up the outside where it get painted, and with the zinc, they couldn't do that. They just couldn't get enough electrode life, and it was just a cosmetic nightmare. So they decided, aha, we've already got a seam that looks like this. It's already got mechanical strength from that. All we need to do is adhesively bond it. So in the early to mid 80s, they were buying, in typical automotive companies, what's the cheapest adhesive you can get? Okay, they didn't put fish glue in, okay, and they didn't put soybean starch in, but they were willing to spend almost $1 a pound for that adhesive. Why? Because the average value of an automobile in terms of manufacturing is about $2 a pound, separate of the health insurance costs and everything else. And that's in the other part that we'll do on the videotape. So they were using $1 a pound adhesives. Well, most of these $1 a pound adhesives, I told you needed about $10 or $15 a pound adhesive to have moisture resistance. And these things were great for about a year until you went into a rainstorm. Now, it wasn't bad in Arizona. There are not a lot of rainstorms in Arizona. But it wasn't so good in parts of the country where your car could get wet. And I saw a number of vehicles from the 1980s where after 4 or 5 years, there basically was nothing other than this mechanical fold holding the inner panel and the outer panel together of those doors, okay? The adhesive was just gonzo. It might still be present, but the adhesive bond had failed. There was nothing. It was just loose in there, okay? And actually it created some problems. So today, they still adhesively bond cars, but they use adhesives that are running about $15 a pound, which is incredibly expensive in terms of what the automotive people think about purchasing things for, okay? $15 a pound is just out of sight. But that's because if you want moisture resistance, if you want an adhesive that's going to last more than 24 months or so, you've got to spend 10 or 15 bucks. If you want one that's going to last 30 years, you may have to spend $100 or $200 or $400, depending on the type of adhesive. So aircraft, Boeing uses $100 a pound plus adhesives, which have all kinds of surface preparation, like anodizing the aluminum and stuff. The automotive companies now have learned to use the $10 to $15 a pound adhesives because they've got to last for 7 years or something like that. Either that or you're going to have to weld some of these things. Okay, that's enough on the adhesive bonding. That's probably most of what we'll do. Actually, I guess I'll say one last thing. Since adhesives are secondary bonds, if you're going to bond with adhesives, you need lots of surface area, and that means you either do lap joints, surfaces to surfaces, overlapped, like sheets and a sheet of paper, or you do things like fiberglass. What's fiberglass? It's glass that's bonded with an adhesive, plastic, right? So you have lots of surface area on the fibers. Or you use particles and then use the adhesive in between. And basically that's your pavement, where you use asphalt to glue the rock together. Adhesives don't work well if you're just talking small contact area in tension or bending or anything like that. You need lots of surface area because it's secondary bonds. All you're doing is you're working with a contaminated surface. You haven't gotten down to metal-metal contact or base metal primary bonds, and that's the problem. Okay, see you tomorrow.